Continuing from where we left off, let's talk a little bit about how in the BitTorrent application we can request and send different file chunks and how we coordinate that with other peers. So in requesting chunks at any given time, different peers have different subsets of file chunks. This is all very dynamic and changes dynamically over time. Periodically, the user, in this case Alice, asks each peer for a list of chunks that they have. Alice requests the chunks from the peers, choosing the rarest first, that is, the chunk that has the fewest copies available. Then, Alice sends chunks to 4 peers. After she receives chunks, she sends those chunks to 4 peers, currently sending her chunks at the highest rate. Other peers are choked by Alice. In other words, they don't receive chunks from her. This situation is reevaluated every 10 seconds. So every 10 seconds, the top 4 peers receiving chunks changes. Then every 30 seconds, the sender, in this case Alice, will randomly select another peer and start sending chunks. We basically, what this is called is optimistically unchoking the peer, and the newly choking peer may join the top 4. So by doing this, we randomly change which peer is receiving which chunk. And what this does is it tends to even out data that's available over the network over time, providing that all the peers remain on the network and send as well as receive. There's another concept called tit for tat. And when tit for tat, when Alice optimistically unchokes Bob, Alice then becomes one of Bob's 4 top providers, and then Bob then reciprocates, and Bob becomes one of Alice's top 4 providers. And basically what this does, it forces over time for you to basically send peers to the devices where you get the best upload rate. And what this does is it basically improves the efficiency of the peer-to-peer network. Next, let's talk about the use of a distributed hash table. So basically, everyone should be familiar with hash tables. That's a very common, basic building block of computer science. If you're not familiar with hash tables, you may want to go back and take a look at that. Then we're going to talk about the concept of a distributed hash table. We're also going to take a look at a circular distributed hash table and how that works. And we'll talk about how that concept deals with the problem of peer churn. So in our discussion, let's start off with a simple database example. So imagine you have a database with basically 2 fields, the key, which uniquely identifies the record, and a value. In this case, we're using a human name for a key, and the value is a social security number. Now this might seem a little bit backwards because usually a key usually in a database is something that's unique, and obviously you can have names like John Washington that can be non-unique. But we're kind of looking at this backwards in a sense because in this case the key is basically the item that's going to be searched. So in this case, you would normally do a search on a human name because that's something that you would have an interest in. So kind of looking a little bit backward from database theory in this particular example. So let's relate this to a hash table. In a hash table, is a convenient way to store and search on a numerical representation of a key. So in this case, we have our key, and basically we apply a hash function to it, and by applying a hash function we get a key that becomes a numerical representation of our text. So in other words, we take John Washington, we apply a hash function to it, and we get the number 8962458. And then we have this value that, in this case, the Social Security number that we want to associate with the key. That's basically what we're going to, the value of the information about the key that when we search for, that's the information that we want to basically retrieve. So when you think about how a peer-to-peer network works, that's exactly what you're trying to do. Each peer has some information, and you have to basically query the peers to find out who has the information that you're looking for. And one of the ways to do that is by using a distributed hash table. And as I mentioned previously, I highly recommend you read the peer-to-peer tutorial that's in the additional information section of this week's learning module, because that will be very helpful in understanding beyond what we're going to talk about in this lecture. So in a distributed hash table, we're going to distribute the hash table information, basically the key and the corresponding value. Basically, we're going to distribute that over millions of peers, and these pairs are evenly distributed amongst the peers. So this allows any peer to query a database with a key, and the database returns the value for the key. To resolve the query, a small number of messages have to be exchanged among the peers. So what we want to do is we want to set this up to keep that number as small as possible. And we also have to keep in mind that each peer only will know about a small number of other peers. What you don't want to do is you don't want to have some large table that each peer has to maintain. So basically you distribute the information, that each peer can try to point you in the right direction until you finally get the data that you're looking for. Also, you have the issue of the fact that since peers are dynamic, you don't want a peer to have outdated data about who has what. So distributed hash tables kind of help out with a situation where you have a lot of dynamic changing of the current peers. In other words, it mitigates against peer churn. So let's talk about assigning key value pairs to peers in a distributed hash table. So basically what you do is you assign a key value pair to the peer that has the closest ID. And the convention is you assign it to the one that's closest, means the immediate successor of the key. So let's say, for example, you have peers who are using ID number 0 through 63. That's the ID that they're using. And right now, currently on your network, peer-to-peer network, you have 8 peers, and their ID values are 1, 12, 13, 25, 32, 40, 48, and 60. So if you have a key whose value is equal to 51, you're going to assign it to peer 60, because as a successor, 60 is the closest successor to the number 51. If the key is equal to 60, then you assign it to the nearest successor, which happens to be 60 itself. If the key is 61, well, there's no more peers after 60 at the current time, so then you have to go all the way to the back and assign it to peer 1. So what this does is this basically evenly distributes the key value pairs amongst the different peers. So in a circular distributed hash table, each peer is only aware of its immediate successor and predecessor. So we have that same example of our peers that we had previously, and they're set up in a circular fashion. So peer 1 is only aware of peer 12 and peer 60. And basically, if you take a look at you have the circle, which is a logical distributed hash table, but this is basically overlaid over a real actual network. So you have this particular host on this, it looks like a cellular network, and this particular host on a cellular network, and they're actually, the next peer happens to be on this, maybe large corporate network, and maybe this peer is as well, and then this peer is, next peer is on someone's home network. So it's basically, in this circular distributed hash table is basically overlaid over a physical network that can actually span many different different networks. So in this case, how do we resolve a query? So since each peer is only aware of a predecessor and successor, if I have key 53, which we know from our previous example is going to be set to be available at 60 because that is the closest successor to 53. So 12 doesn't go right to 60 because 12 is only aware of 1 and 13. But he knows that 1's in the wrong direction. So he sends a request to 13. 13 sends a request to 25. And this happens over and over again until you finally get the peer that has the value associated with key 53. And then peer 60 can send that directly to the requesting peer, which is peer 12. Sometimes you can have circular distributed hash table with shortcuts. In this case, each peer keeps track of the IP addresses of a predecessor, a successor, and a shortcut. And so what this does is basically in the physical case of this example compared to the previous page, this cut down our queries from 6 messages down to 3 because basically 12 had a shortcut to 32, and since it knows that 32 is going to be closer to where 53 is than its predecessor, is sent it right to the shortcut. 32 had a shortcut of 48. Using that same logic, it skipped right to 48, and then 48 queried peer 60. And in general, it's possible to design a distributed hash table with shortcuts so that if you have O log n neighbors, you will have O log n messages in your query, which is better than a straight circular distributed hash table because in that case you're going to have O to the n, O times n messages instead of O log n as we have over here. Okay, let's talk a little bit about peer churn. So one of the issues is obviously, since peer-to-peer networks are dynamic in nature, peers may often come and go. People don't keep their computers on all the time, or someone might lose network connectivity. So basically, to deal with that, each peer knows the address of two of its successors. So the nearest successor and the one after. Each peer periodically pings its two successors to check to make sure that those successors are alive. If the immediate successor leaves, then chooses the next successor as the new immediate successor. And this way, we keep up the accuracy of our distributed hash table, our circular distributed hash table, even as peers come and go. So here's an example. Peer 4, so we have over here, peer 5 abruptly leaves the network. So peer 4 is aware of peer 5 and peer 8. So what happens? So peer, using this peer churn example, peer 4 detects that peer 5 is gone. It was aware of peer 5 and peer 8. Now it makes 8 its immediate successor. Then peer 4 asks 8 who its immediate successor is. Since each peer has two immediate successors, it can now 4 can ask 8 who its immediate successor, and now 4 can assign that value, in this case 10, to be its second immediate successor. This is all that we're going to discuss today on peer-to-peer networks. Like I said previously, I highly recommend you read over the peer-to-peer tutorial. I know it's a little bit outdated, but the concepts, the general concepts still apply, and it's definitely worth reading. Now we'll conclude this lecture, and then next we will discuss socket programming.